Hello everyone. In this video, we get to talk about a brand new coordinate system that we'll be using for this section and for the very last section of Math 1080. And it's called the polar coordinate system. And so the coordinate system that we've done back in the day is called the Cartesian coordinate system, where we have direct distances for two points, and they're both on perpendicular axes. Newton back in the day, though, he described a brand new coordinate system called the polar coordinate system. There we go, coordinate system. And to give you the gist of what a polar coordinate system can help us define, it essentially allows us to graph the path of a function around a circle, essentially. And so let's go ahead and start defining some stuff before we play around with the polar coordinate system. In the polar coordinate system, the origin that I'm going to use is typically referred to as the pole. And for most of these examples, you'll see O to label the origin or the pole. So in this section, I'll use pole and the origin interchangeably. And then what people do is you draw a ray from the origin, and that is called the polar axis. And what that is doing is that's telling us where does this angle that I'm going to draw begin. And so the way we're thinking about a point in the polar system is when I see the value r, it is the distance between the pole and to that new point that I just described. And the angle theta is going to be the angle that is measured between the pole and that new point that I described. And so that ordered pair, r and theta, are the distance between my pole and the new point P, and the angle that measures that between those two. Those are going to be called my polar coordinates of P. And now let's go ahead and do some terminology to define what that is. For the value r, what I'm going to use to refer to that is called the radical coordinate. Or in other words, the point is r units away from r distance away from the pole. And the angle theta in polar coordinates, that's referred to as the angular coordinate. Now, mathematicians are not creative, so angular for an angle. All right, and so let's go ahead and start thinking about if I was plotting a polar coordinate, how will I do that? The way that I think of plotting a polar coordinate is whatever the radical coordinates are, what that is referring to is the distance from it. And so what I'm thinking of is whatever r is, that is where I'm going to begin drawing my point. And then whatever angle theta is, I'm going to rotate that many units in radians and that would be my point in my polar coordinate. So the way I'm going to plot a polar coordinate is on the horizontal axis, I'm going to begin at whatever value r is. Then I'm going to rotate based off what the angle is doing, is telling me. If I have a positive angle, just like with the unit circle, if an angle is positive, we're rotating counterclockwise. But if my angle is negative, I'm rotating clockwise. So the same convention that we've used back in trigonometry when we learned about the unit circle. Okay. And so now let's go ahead and do some shortcuts for about r and theta. So here's the thing that I'm thinking of. Let's say I have a negative value for the radical coordinate, and I want to rotate phi units, and I'm going to assume that, or theta units, and I'm going to assume it's positive. So if I have a negative value for the radical coordinate, and I have a positive theta, I'm still going to rotate. By that meaning units that plot the point. But the thing that I want y'all to note as well is, if I have a positive theta, then if I'm taking my r as the points on the horizontal axis, and theta as the vertical axis, then if I have a radical coordinate less than 0, it's going to be on the opposite side of the pole. And you get a better explanation in figure 2 above. Is, let's say here is r and theta. If I say that my radical coordinate is negative, I essentially flip this over 180 degrees from that. So my convention is, if the radical coordinate is positive, the point's going to lie on the same quadrant as the angle. And then if the radical coordinate is negative, it's going to lie on the opposite side of the angle theta. And so that's how I'm thinking of it. Now, one thing I do want to note, and I'll say this from angle 2, or from part 2. Another way that you could think of a relationship between them is the polar coordinate negative r theta is always equal to r theta plus the angle phi. And why is that? So here's kind of the dot process. And I'm going to extend this photo above to kind of make it clearer. So as mentioned before, negative r, that's where I begin. And I go to whatever angle theta is. Let's try to match with that point. And now, what this equality is saying is that is equivalent to me saying, let's pretend that negative r is positive and is r theta, so the line in black. If starting from here, I go 180 degrees. Let's use a different color. Let's use purple. If I go 180 degrees, which if you convert pi from radians to degrees, pi will be 180 degrees. I land back at the same ray that is generated from me starting at -r and then going pi units. So that's going to be an equality that I will be abusing in the next example. So before we start anywhere, let's practice how we're going to plot the points with the following polar coordinates. And for reference, the point in part A will be P. The point in part B will be Q. The point in part C will be R. And the point in part D will be S. And I'll use the following colors that you see to refer to each individual point. Let's see how this is going to look. Sometimes with a polar coordinate, you might see Git's coordinate system before. And this is used solely for drawing the polar coordinates. And so in this context, I'm going to assume that in radians, that should be pi over 6, that it is split evenly by a unit of 6 or something like that. Okay? So if I continue on, that will be 2 pi over 3, that will be 5 pi over 6, and so on. And so I'm going to go with that assumption for this. And I'm also going to assume that each one will be half a unit. So this circle corresponds to the radius 1/2, 1, 1/2, 1.5, 2, 2.5, and so on. And so let's figure out how we're going to draw these points. So the first value, A, is an R value or a radical coordinate of 1, and then an angular coordinate of 5 pi over 4. And so what that means is I know my distance from the pole is going to be 1. So I'm going to start off at 1, and then I'm going to rotate that point 5 pi over 4 radians. So 5 pi over 4, what that means is I rotated 1/2 of the circle. I'm a little bit over. Hit the 7 pi over 6, and I end up somewhere around here. Oh, and that's 1.5. So let me, there we go. And now I'm back at 1. And that will be my point P. So, like I said, the way I did this was I started at 1, I rotated 5 pi over 4 radians counterclockwise because my angle is positive, and I ended up, I erased it, at the point P. So let's repeat that process with the point Q. I have 2 times 3 pi, so 1/2, 1, 1.5, 2. So I'm going to start up here, and it says I rotate 3 pi radians. Keep in mind that a circle, we want to have 2 pi. That means I did 1/4 rotation about the circle, and then I performed another rotation for the extra pi unit, which means I end up there. So let's erase that to make that clear. And there's my point Q. Now let's do R. Again, I also start off at 2. But for this example, I have an angle of -2 pi over 3. So what that means is I'm going to rotate clockwise 2 pi over 3 units, or radians. So there's my negative pi over 2 radians. There's my, and then there's my 2 pi over 3. So that means R ends up here. And there we go. And now let's go ahead and draw S. So keep in mind that there are two ways to draw and plot where S is because I have a negative radical coordinate. The first way to start off, because I start off at negative 3, I will start off here. And from this point, I'm going to rotate 3 pi over 4 radians. And because it is positive, that means I'm going to rotate it counterclockwise. So there is pi over 2 rotation. And there is another 4th radian rotation to give me the value for S. Let's draw that back. There we go. So let's go ahead and draw this again using that remark above. This is saying it's the same as starting at 3, ending up at 3 pi over 4 plus pi, which if you do that, I get 7 pi over 4. So let's see if we land at that same point using that identity. So now I'm going to start off at 3, which will be right here. Rotate pi radians. And then I rotate another 3 pi over 4 radians. And I land at that same point. Corresponding with, let's draw that orange dot again. Corresponding with that remark that if I have a negative radical coordinate and theta, it's the exact same as me starting at the positive radical coordinate, but I add pi to whatever angle I have. And because there are two different ways I could have gotten to point S, that's going to be one difference between our Cartesian coordinate system and a polar coordinate system. Polar coordinates, they have more than one way to represent that point. I mean, in part D, I represent x as negative 3, 3 pi over 4, or 3, 7 pi over 4. And with that same idea, I can actually represent our first point in this example from 1a as follows. I kept the same point 1, didn't change the radical coordinate, but instead of rotating counterclockwise 3 pi over 5 pi over 4 radians, I now rotated clockwise 3 pi over 4 radians. What I did here was radical coordinate stays the same, but what I've done is I got 13 pi over 4, which is what you will get if you add 2 pi to 5 pi over 4. And so what does that mean? That means I did one full rotation around the circle, and then I rotated again 5 pi over 4 radians. And now this example is taking the fact from before. And this is negative r theta, and that's the same as changing it to a positive and taking your angle and adding pi to it. Because if I add pi to pi over 4, I'll get 5 pi over 4. And with that, we can actually use the following to represent any polar angle. If you have a positive radical coordinate, I can always represent the point r theta by keeping it the same sign, but theta plus 2 times an integer times pi. And that's corresponding to the periodicity of sine and cosine. And I can also do the following. Switch to sign negative, but now add theta, the angle that I have, to 2 pi plus 1. So 2 times the integer plus 1. And the reason why that plus 1 is there is that's corresponding to that property from before, that if I rotate by an extra 180 degrees, I get back that point. So that's where that plus 1 is coming from. All right, and with that, let's practice different ways to represent a polar coordinate. So let's express the polar coordinate 2 and then pi over 4. So what that meant was I started at 2 and then I rotated pi over 4 radians. Well, by what we talked about before, there are 3 different ways we can do it. One way we can do a different representation is I can add 2 pi to x, and that does not change the point. Because the extra 2 pi, all that means is I did 1 full rotation around the circle, which will be 9 pi over 4. And so for reference, here's a picture to refer to that. Another way that I can represent this is I'm going to now use the identity negative r theta equals r, or the radical coordinate, and then I rotated by an extra 180 degrees. And I could go backwards with this if I started with a positive radical coordinate to a negative. So I start off at negative 2, but I rotate pi over 4 plus pi to give me negative 2 and then 5 pi over 4. So the way that looks like in this photo is now I begin at negative 2. I rotate 180 degrees to correspond with pi, and then I rotated an extra pi over 4 radians. And then the other way that I can get to this is, what if I rotated clockwise? Well, because our original coordinate was pi over 4, let's go ahead and want to look like if I wanted to rotate clockwise. And the way I would do that is subtract by 2 pi. So I get pi over 4 minus 8 pi over 4. So I get negative 7 pi over 4. To have equivalence. So what that means is I start off at the same point too, but instead of rotating counterclockwise as we would before, we now rotate it clockwise by 7 pi over 4 radians. And that is in a nutshell how we're going to plot polar coordinates in our new system. But now let's say I want to figure out how I want to relate a polar coordinate with a Cartesian coordinate. And I say that this is one of the reasons why we care about a parametric equation. So pretend I have the following polar coordinate that I have, which is r. So if I have my horizontal axis and then I pretend I drew vertically up, I have a right triangle. And so with that, I can form the equation of a circle. The equation of a triangle by Pythagorean theorem. And the reason why I said circle is, as y'all gathered, polar coordinate means I'm kind of rotating. This is the equation of a circle with radius r, which is corresponding to our parametric equation of a circle before. And also from this, we can also generate how we're going to calculate x and y. Because if I have a right triangle, well, cosine is adjacent over hypotenuse. Adjacent is x, and r, which is my radical coordinate, is treating as my hypotenuse. So x over r, and the same idea with sine of theta, which means I can explicitly solve for x and y. So x gives me cosine of theta, or r times cosine of theta. Y will be the radical coordinate times sine of the angular coordinate. And this is how I'm going to convert to Cartesian. Well, how am I going to... Well, let's say I want to go the opposite route, and I have Cartesian coordinates, but I want to convert to polar coordinates. Well, I could get the radical coordinate very quickly from that equation. By Pythagorean theorem, I have that the radius, that the radical coordinate r squared is equal to x squared plus y squared. And to avoid ambiguity, because we initially think of r as the distance between the point P and the pole, for this conversion, I am going to assume that r is non-negative. And that's to avoid, when I take the square root of it, that avoids me from contemplating about the negative answer of the square root. Now, how am I going to get the angular coordinate? Well, if I'm given the Cartesian coordinates, I know what x is and what y is. And in terms of that right triangle diagram, I should know what tangent of theta is, because tangent is opposite over adjacent, or in case in this photo, y over x. And we're going to use this relationship to gain the angular coordinate for our polar system, which is summarized here below. So to summarize, if I have polar coordinates and I want to convert to Cartesian, I'm going to use the following parametric equations in equation 1. But if I'm given Cartesian coordinates and I want to convert to polar coordinates, I'm going to use the following system of equations. You can think of it as the equation of a circle of radius r to get the radical coordinate, and then tangent over opposite over adjacent to get the angular coordinate. So before we go through some examples, there are a few remarks that I do want to make. The first one is, when you have a Cartesian point and you're trying to find the angular coordinate, my advice before you do anything is determine what quadrant your Cartesian point is. And the reason why I recommend that this is going to tell us which coordinate my angle should end up in. So for example, let's say I'm back in my Cartesian coordinate and I'm given the point -1, -1. Well, if I calculate tangent of theta using our equation, I'm going to have +1. And we know that there are only two angles that gives us tangent of theta equals 1. That's going to be at pi/4 and at 5 pi/4. And to avoid that ambiguity, because I know a priori that my Cartesian point lands in the third quadrant, that means my angle is going to land in the third quadrant, and so I'm going to choose 5 pi/4 for my angular coordinate. Another common mistake that I've seen before, and I want to say to avoid, because I define tangent theta as y/x, a very tempting thing that a lot of people do is that they say that theta equals arctan of y/x. I cannot emphasize enough that this does not always work, and that's because of the range of arctan. So, if you recall from back in Cal 1, what this interval is saying, -pi/2 to pi/2 open parentheses, is on my unit circle, I'm only looking at the right half of my unit circle, excluding the endpoints. And for me to do this sort of relationship, I have to know that my angle theta is in between -pi/2 and pi/2. For the example that I made above, it won't work in that scenario for me to do that. In that case, I would have concluded that I would have pi/4 because that was in my range, which is off from what I mentioned in remark 1. All right, let's practice some converting some polar to Cartesian. So because I'm converting from polar to Cartesian, I'm going to use that as r. I'm going to use pi/3 as theta. So now using our Cartesian coordinates, I'm going to have x is equal to r, which is r times cosine of theta. After substitution, I'm going to substitute 2n for r. I'm going to substitute pi/3 for theta. Cosine of pi/3 is 1/2. And I should have 1 for my value. Now let's do that again. Oh, there we go. For y. Again, that is the parametric equation r times sine of theta. Again, I'm going to substitute in 2 for r. I'm going to substitute in pi/3 for theta. Sine of pi/3 is √3/2. I get √3. So that means we get the Cartesian point (1 √3). So now let's go backwards and say, let's say I want to now convert from a Cartesian coordinate to a polar coordinate. So first thing I want to observe is I want to figure out what quadrant the point 1, -1 is in. Because my x value is positive and my y value is negative, that tells me that this point is in the 4th quadrant, meaning that whatever angle that I get for the angular coordinate should be an angle that lands in the 4th quadrant. Alright, so let's go ahead and figure out what r is. So using our equation, r squared equals s squared plus y squared. I'm going to substitute in +1 for the value for x. I'm going to plug in -1 for the value of y. I'll get 1 + 1, which equals 2. And again, taking the square root and assuming that the radical coordinate is non-negative, I get that r equals square root of 2. Now let's find the angular coordinate. Tangent of theta is opposite over adjacent. So -1 over 1, which is a -1. And so there are two values that could give me a -1 that we know. I get a tangent of -1, both the 2nd and the 4th quadrant. So that means theta could either be 3 pi over 4 or 7 pi over 4. But because I already observed that the Cartesian coordinate is in the 4th quadrant, 7 pi over 4 is going to win. So I'm going to make that note. And I'll make that note in purple. Since our coordinate point 1, -1 is in the 4th quadrant, theta is going to equal to 7 pi over 4. Now, as I mentioned before, polar coordinates have multiple representations. So there's another value for theta that I can get to land in the 4th quadrant, and that is if I decide to rotate clockwise pi 4 units. So because of that, two possible answers. For you are the radical coordinate of 2, square root of 2, and the angular coordinate of 7 pi over 4. Another possible answer is square root of 2 negative pi over 4. And again, if you want, you could do square root of 2 and then add pi to the angular coordinate and get another value. That's perfectly reasonable as well. So just keep in mind that, going back to our equation for converting, yes will give us, so converting from polar to Cartesian will give us unique points. Meaning, so if I plug in a value for r and I plug in a value for theta, I will get a value for that. However, for the Cartesian to polar conversion, I'm not unique because of the angular stuff. So keep that in mind, that as made in that remark, polar to Cartesian will be unique, but Cartesian to polar in terms of the angular coordinate will not be unique. So there's it for converting from polar to Cartesian and vice versa. So now let's talk about polar functions or polar curves. Because after we learned Cartesian coordinates back in the day, the next thing your teacher probably told you to do was let's start making functions for that. So for example, if I gave you y equals 2 and asked you to graph it, what we learned way back in middle school or for that is we would say go 2 units up and then draw a horizontal line. And so we're going to figure out how we can sketch a polar function for that. And in this case, a polar function, or the other name, a polar curve, is going to be represented by the function where the inputs are the angular coordinate and the output is the radical coordinate. So that's already different from Cartesian, where the value on the horizontal axis is my input typically, and the value on the vertical axis is my output. Here I kind of switch vice versa for that. And the reason why polar curves are represented like that is a lot of the polar curves that we're going to deal with are going to be based off of angles. And so we're going to learn how to play around with that. But before we get into something complicated, let's start with something simple. And let's start saying what happens when we represent the polar equation. The radical coordinate is fixed at 2. So here's kind of what's going on. So as mentioned before, the radical coordinate kind of tells me, 1, where should I start rotating, and 2, the distance between the new point and the pole. Well, in this equation, r is fixed, but theta is not fixed. Meaning, if I want, as long as I have that the radical value coordinate is 2, anything along this curve is a valid point for that polar equation. It doesn't matter what angular value I get, and that all of them are valid as long as r equals 2. So if I have a polar equation where it's just the radical coordinate equals 2, this is going to represent a circle with the center being the pole and the radius being 2. And so in general, if I have an equation r equals some fixed number, that polar curve is going to represent a circle with the center being the pole or the origin, and a radius being the absolute value of that number a. That's to correspond to, say, if I have -2, for example. Same thing. That's why, if you heard in the video, I used I said radius, slip of my tongue. And that's because I could think of r as, hey, this is the radius of a curve that I start to form. So now let's go vice versa and say, now I have a polar curve, but instead of the radical point coordinate being fixed, the angular point is being fixed. So I'm going to make that as a note. So now I switched it up on now. I now say that the angular coordinate is fixed, but r is not fixed. And so now, in that regard, what will the curve look like? It's going to be the same thought process as the previous example, where as long as I have that the radical coordinate is 2, I'm good to go. Same idea here. As long as I have the angular coordinate to be whatever theta is, any values for r would be fair game. So as long as I have this point, that's still valid. But I can also say that this point is valid as long as the angular coordinate corresponding to that point is theta. So for example, if I said this angle was 1, then these points will be 1, 1, radius 2, but angle is theta. And I could keep going along, where if I say, now let's say r is 3, but it's still 1, so on and so forth, as long as I keep that going. I can also go negative if I want to. But if I want to go negative, keep in mind that I am crossing the origin. And the reason why I'll be crossing the origin, that means I start off at 0, and I'm trying to rotate about the origin, but because that's my center, I'll be rotating around nothing. So, and I keep on going. And like I said, as long as I rotate whatever theta is, that line is going to be a valid line. So, if I have where theta, or the angular coordinate, is fixed, but the radical coordinate is not fixed, it's going to give me a straight line. So this curve, I spelled curve right. This curve will be a straight line that passes through the origin. As long as that angular coordinate is still the same, I don't care what r is. Which in that case, this curve will just generate a line. Well, let's now get a little bit more exotic. Let's change it up in this case. Let's say I want to sketch the following curve this way. We're going to learn a more sophisticated way to do this, but right now we don't know it. And because I don't know a clever way to deal with this yet, I'm going to have to go back to basics and explicitly write out the inputs and the outputs. So my inputs are theta, and my outputs of r equals to a function with inputs of theta, which is 2 times cosine of theta. So if I plug in 0, 2 times cosine of 0 is 1, so I should get 2. Pi over 6, I should just split my output for r to be square root of r, but square root of 3. Pi over 4, I should have an output of square root of 2. For pi over 3, I should have an output of 1. For pi over 2, I should have an output of 0, and so on. And that's going to be corresponding over here. So I have an angular value of 0. So I should have a radical value of 2. So that one's checked off. I have an angular value of pi over 6. So I should expect an output of square root of 3. At pi over 4, rotate until I hit there. I should be at the radical coordinate square root of 2. Same thing, as continuing to pi over 3, I should get to 1. To pi over half, I should land at 0. And it continues for as long as I do that. So keep in mind that I have a circle Fergus graph. So because of that, let's figure out if I can find the Cartesian equation for Yitz. And I'm going to base this off of the parametric stuff that we talked about before. So here's going to be my thought process. I know that x is equal to r times cosine of theta, which means I could quickly solve that and get that x over r should equal cosine of theta. And what does that mean? That means I have the equation x over r equals cosine of theta, which means if I multiply by 2, I have that my function r equals 2 times x over r. So I want to keep that noted, that I now have r equals 2 times x over r, meaning if I square r, which means I multiply by another r, then on the right hand side the radical coordinate cancels, and I now have r squared equal to 2x. So now, using my polar to Cartesian stuff that I know, and vice versa, I know that r squared equals to s squared plus y squared. But I now know that r squared should equal to 2x. And if I move 2x to the right-hand side by subtracting, I now have 0 equals 2 x squared minus 2x plus y squared. That doesn't look like anything that I know, but because of the curve that I have, I should have a circle, which means I should have something squared plus another something squared equals something else squared. And so the y squared part is taken care of, but not the x's. So let's see how we can take care of that. And the way we're going to take care of that is using a tool that we haven't used in a very long time, and that's complete the square. So I have x squared minus 2x. Again, to recall how we complete the square, I find the coefficient in front of the x. I want to take 1/2 of the coefficient that is with the x, and then I'm going to square that at the very end. And what that's going to give me is I'm going to add 1 to it. And the reason why is I can rewrite that as x minus 1/2 of that coefficient, all of that squared. But to maintain equality, because I added that new number 1, I have to also subtract by that new number. So that is x minus 1, all of that squared, and then a minus another 1. So back to our work, we should have now x minus 1 squared minus 1 plus a y squared equals 0. Because that minus 1 is not paired with inside a square, I'm going to move it over to the right hand side, and I get 1 equals x minus 1 squared plus y squared. And now I have something squared plus something else squared, one with respect to x, one with respect to y, equals a number squared. So I now have the equation of a circle. So what does that tell me? It tells me the polar curve that we were playing with in part A is a circle, and it has a radius of 1 and a center of 1, 0. And so I can use that to help me figure out the equation of a circle. So let's extrapolate that real quick, and let's use that same methodology to also find the equation of a circle to Cartesian coordinates. So first let's write down r equals 10 times cosine of theta plus 24 times sine of theta. So if I'm ever trying to do this type of problem and I have sine and cosine, my methodology or my thought process always for these problems is always go back to our parametric equation for a circle that we learned before. So I need an r multiplied to this cosine and this sine in order to substitute in for x and y. So that means I'm going to multiply r to both sides of that equation, giving me r squared equals 10 times r cosine of theta plus 24 times r sine of theta. And that is x by my parametric equation, and that is y by my parametric equation. But I could go even further and substitute more, because I have the equation of r squared equals x squared plus y squared. So now I have the equation x squared plus y squared equals 10x plus 24y. So I'm now going to do the same idea in the previous example. First I want to move the 10x and the 24y to the other side of the equation. Kills off those two, and I now have x squared minus 10x plus y squared minus 24y equals 0. Let's do a next page to go over to complete the square portion of it. complete the square. Okay. So x squared minus 10x. So in this case, my coefficient with x is 10. So now I have to do 1/2 times 10 to give me 5. And so for completing the square, I need to square this value, which will be 25. So x minus 10x. I add 25 to that, and I also subtract 25 to that. And complete the square tells me that this portion will equal x minus 5 squared. Meaning I should have x minus 5 squared minus 25. Alright, and let's do the same idea for the y squared minus 24y. In this case, 1/2 of 24 is 12. 12 squared is 144. So y squared minus 24y minus 144 plus and minus, got them mixed up, plus minus 144. And this should equal y minus 12, all of that squared, giving me a final answer of y minus 12 squared minus 144. Alright, and there's our two expressions after completing the square. So let's go ahead and substitute that back in to our work. So I now have x, let's stick that to black, x minus 5 squared plus y minus 12 squared. And what I'm going to do now is I'm grouping those two leftover numbers on the end. 25, negative 25 minus 144 gives me negative 169. Want to add it and move it to the right hand side, leaving me with the equation x minus 5 squared plus y minus 12 squared equals 169, or another way to express 169, 13 squared. So this curve tells me that the polar curve is a circle with radius of 13 and center 5, 12. I don't need that comma. And there's our description of that curve. And this also describes something in general for a circle for a polar coordinate. As mentioned in one of the previous examples, if I just have that the radical coordinate equals a number, but the angular coordinate is not fixed, this is going to describe a circle with radius absolute value of that number centered at the origin or the pole. If I'm taking a general equation of the form r equals 2 times a number a times cosine of theta plus 2 times a number b times sine, this is going to describe a circle of radius the square root of a squared plus b squared, centered at the point A, B. And let's look back at example 8. Well, 5 and 12 popped in here because 10 is 2 times 5. And let's get rid of that. There we go. And 24 is 2 times 12. So that form still played a part for that. And 169, well, that's definitely 5 squared, 25 plus 12 squared, which is 144. So we actually were able to play around with that for yits. So the next topic for your section is, now I don't want to just plug and chug points that I did before. That's very time consuming and that's very annoying. So let's figure out how we can graph polar curves and figure out what's going on. So here's going to be our Cartesian to polar method for graphing the polar curve. What I would do first is I'm going to graph the polar curve, whatever is defined, as if it was a Cartesian coordinate, where I'm going to treat the angular coordinate as my horizontal axis and r as my as my vertical axis. Now, one thing that is helpful is make sure that when you're working, you choose an entire interval where this curve is produced. And that's going to be determined by the curve. So say, for example, I had r equals cosine of theta. In that case, we learned, and I wanted to graph this in polar coordinates. We know it's a circle now, but let's pretend we didn't. Because I know that cosine is periodic with period of 2 pi, what that's going to tell me is that I'm going to restrict my angle to 0 to 2 pi. And that's because after I hit something greater than 2 pi, well, periodicity means that I just reset every time I hit 2 pi. So I don't get anything new after 2 pi. So that's what the first part is saying, highlighted in blue. And from yet, I'm going to use that curve as a guide to sketch the final polar curve. And so let's check how we're going to do that with the following example. We're going to sketch the polar curve, r equals 1 plus sine of theta. So first I'm going to pretend that I'm graphing a Cartesian coordinates. And if that was the case back from before, it's just my sine function shifted up by 1 unit. So I'm going to determine my interval that I'm working with. So because sine is periodic with period of 2 pi, I'm going to work in the interval 0 to 2 pi, because as mentioned before, since I know my function is periodic, I'm not going to get anything new about my curve if I go outside of that interval, because it's just going to be a reset or a repeat of this picture. And so now let's follow step 2, and let's see what's going on. And it's going to be based off of how we're going to increase and how we're going to decrease with that. So, from 0 to pi over 2, one thing that I note is that I am increasing from 1 to 2. And so here's kind of what that means if I was plotting it. Is that I'm going to start off with a distance of 1. And this is going to be my starting point. Let's pick a different color than pink. There we go. I'm going to rotate pi over 2 radians and make sure that wherever I ended up on, it is a distance of 2 from the pole. Here's a picture to represent that, to make it more accurate. So note that my curve is definitely not looking like a circle, or I shouldn't say that because it does look circular. What I mean is my distance is not 2 on the horizontal axis, so it's not going to be so my final curve is not going to be a circle that we're used to dealing with. So now let's keep going on. Oh. Now I'm going to graph from pi over 2 to pi. I note that I decrease from 2 to 1. So if I was going to go back here, it'll look something like that, where that distance is 1. So there's the next photo for that. Next thing I'm going to note, from pi to 3 pi over 2, I decrease from 1 to 0, which means from this original point, I'm going to land at the pole. And then as I go from 3 pi over 2 to 2 pi, I increase to 1, meaning from the pole, I land back at 1. And put those together, and that gives us our polar curve. Now, fun fact about this, this particular polar curve actually has a special name, and is called a cardioid. The reason why is because it's shaped like a heart. Alright, and let's keep going. So now let's say I want to sketch the curve r equals cosine of 2 pi. So as before, because r equals cosine of 2 pi, we're going to restrict to 0 to 2 pi. And the reason why we're going to go to 2 pi instead of pi is to continue on with that. So let's still make the same observations as before. So if I go from 0 to pi over 4, I decrease from 1 to 0. Meaning, starting at 1, I hit the pole. So that's going to be curve 1. If I go from pi over 4 to pi over 2, I'm going to decrease from 0 to -1. So that means from my original point, I'm going to keep rotating until I hit -1. And then if I kept on following that pattern, I would increase from, say, -1 to 0. That would be what the curve tells me next. And I land there. Now, I increase from 0 to 1, but because I end up at pi, I would end up, well, let's go ahead and do that. And we end up over here. And this pattern will keep on going throughout. And at the end, you're going to end up with something like yes, which is a pretty gnarly thing. And to me, it looks like a flower petal. And the first people who made this parametric curve, they thought so too. And so this curve is going to have 4 loops. And because it looks like a flower, people call this curve a 4-leaved rose. Let's make that D look a little bit prettier. There we go. And now the last thing I want to mention for polar curves and polar coordinates is symmetry. And so let's talk about that. So the first thing I want y'all to note is symmetry about the x-axis, or the horizontal axis. And this is going to occur if this happens. If I look at the curve, and if I reflected by the horizontal axis, I get a mirror image. That's symmetric about the x-axis, and that's reflected by the only difference between these two polar coordinates being that the angular coordinates differ by a sign. So next thing is symmetry on the vertical axis, and this is going to occur whenever this will occur. If I have that, this should be R. If I equal, now I have negative R, which means I start off on the negative values for R, and if I rotate clockwise. Now one thing I want y'all to want to make a point for this, this will be helpful in 12.3. What some textbooks use call this symmetry. They use this in my textbook when I was an undergrad. They usually say symmetric on y equals pi over 2. And that's corresponding to that vertical line, which if I rotated would correspond to if I rotated pi over 2 radians. And I get a third symmetry, and that's symmetric about the origin, by using that identity from below, where if I have a negative radical coordinate and I rotate counterclockwise theta radians, it's the exact same as if I have the opposite sign and I add pi to my theta radians from before. And so those are going to be our 3 symmetries for polar curves. All right, and that concludes section 12.2. In the next video, which is our last video, in the last section for Math 1080, we're going to learn how to do calculus on polar curves and polar coordinates. Have a great evening, and I hope y'all are having a fantastic day.